Good morning. Welcome to Krishna's classroom. Let us continue to explore the concept of convergence in measure. And one of the obvious questions that you would ask is this: does convergence of measure imply pointwise convergence? Now, the example that we analyzed last time, just briefly recall it, immediately tells you that this is not so, because there exist sequences which converge in measure but does not converge pointwise anywhere. Now this is very fascinating. So the example that we have looked at is this. So you take the interval 0, 1. It's a very nice way in which you divide. So this is step 1. And then you define a function as f1 to be the characteristic function of 0, 1 restricted to the interval 0. That's identically equal to 1 on this interval, so there is no problem. Now the step 2, in step 2 we construct two functions. Divide this at half, and then you have two functions defined, f2 as the characteristic function of 0 to half restricted to the interval 0, 1, and f3 as the characteristic function of half to 1 restricted to 0. So two functions are constructed. So you have f1 here, f2 equal to 1 here, f3 equal to 1 here, elsewhere 0, everywhere. Now what is the next thing? Take the same interval 0, 1 and divide this into three parts. 1 by 3, 2 by 3. It's a very fascinating example. And then define three functions. f4 as obviously f5 define as and f6 defined as characteristic function of 2 by 3 to 1 restricted to 0. So how many functions we have now? We have now 6 functions. Okay. Now obviously you can continue this process by dividing this into 4, dividing this into 5 and so on. And at the mth step, to divide this into m equal parts. Okay. So you have 1 by m, 2 by m, k by m, and 2 and here of course 1, and so on. So the condition is that 1 less than or equal to k less than or equal to and then we define m functions. Okay. So the first function is 1 here, second function is 1 here, etc. Third function is 1 here, and so on. So you can define these kind of functions, sequence of functions. So eventually what you define a sequence of functions. Now you observe that as m and n together goes to infinity. Okay. So Fn is defined on the interval 0, 1, n and m goes to infinity together. So at each stage you are defining the interval 0 to 1. So you get this sequence of functions. Now what we have proved is the following. That is, we have shown that converges to 0 measure. But at no x, point is. Okay, it's a very fascinating example. Take any x. Now what happens is that you may get a string of zeros, but then suddenly a 1 would appear. It's very simple to explain. Suppose you take a point that lies between 1 by 3 and 2 by 3. And maybe say you take the point, say something like, or let us look at what happens at some point here, that lies between 1 by 2 and 2 by 3. Then what happens? This one here. So the sequence that you get is 1, then it is 0, then it is 1 again, then you see you go to the next breakup, you are going to get a string of zeros, and somewhere you will get a 1, and so on. Okay, so you cannot avoid this. You may get a feeling that lot of as m increases, you see that n increases equivalently. See that the zeros would start, more and more zeros would start coming. But the whole game is spoiled by the appearance of a 1. Therefore, the convergence does not happen. Okay, that's quite clear. So it does not converge pointwise at any point on this interval. Right? So this is an example which says that convergence in measure. So what is happening here? See, the sequence of curves which are of this form. What is the sequence of curves that you get on the interval 0 to 1? You have, see, this is your F1. That is the graph of F2. What about F2? F2 is this one with 0 here. This is your F2. Okay. F2 is this. And then F3 is what? F3 is, I'll put another color here. F3 is this here. Then it is 0. F4 is from 1/3 to 2/3 it is 1. Elsewhere it is 0. And F5 is 1 between 2/3 and 1, and elsewhere it is 0. Now this is how the functions are defined. Okay. Right? I can easily verify the facts that I have said. And what it says is that at no point this sequence converges pointwise to 0. However, these graphs of these functions would get closer and closer to 0, 1, and it hugs 0. Okay? Right? It hugs 0, but it doesn't merge with it. If you want to some fancy terms to be used for that, then this is what it is. Okay, so I would put it this way. Equal to 0. Infinity, but does not that's the most interesting way in which I can put it. I don't know, maybe I am wrong or I am right. I have not seen this expression anywhere. So it doesn't immerse into f equal to 0, but it goes and hugs 0. This is a very interesting phenomenon. So this is what you call the convergence in measure. So convergence in measure does not necessarily assure convergence pointwise. Okay. Now this is the conclusion that we make. So in our string of convergence that we have looked at, see, he said you have uniform convergence, it implies convergence pointwise. Convergence pointwise implies convergence pointwise almost everywhere. That's obvious. And the convergence pointwise almost everywhere implies convergence in measure, but it doesn't happen the other way. Okay? So let us ask what best you can expect under this scenario. Okay? Now I'll just cite or we will extract from this a subsequence. Okay? So let us explore that. define the sequence as follows. Namely, see this G1 equal to G2 equal to chi of G3 defined as and so on. Now it is clear. The next one is going to be this. So the general term Gn is going to be chi 0 to 1 by n restricted to 0. This is the general term and so on. So you observe that the sequence Gk is a subsequence of Fn. It's a subsequence of Fn. What can you say about Gn? Now you observe that, it's quite easy to see. Easy to observe this. Gn converges to 0 pointwise only. Not everywhere, possibly. No. Okay. Let us work on this. Now what happens? Now you see that Gn converges to F identity 0 or 0 1 almost pointwise. At the point 0, possibly it does not converge at all. Because you see that the value 1 would, the string of zeros with 1 appearing over and over again. But then, no, it's not frequently. You cannot say that it's all going to be 0 from some stage onwards. It is not true. But you can still find another one. So it is pointwise almost every. That means where of course it doesn't converge at all. Okay. That is fascinating. So in this example, we observe that although the sequence converges in measure to 0 function, it does not converge anywhere pointwise, or even it doesn't converge even pointwise almost everywhere. Still, you have a subsequence which converges pointwise almost everywhere. F equal to 0. And this is not the only subsequence. You can use the same technique to construct other subsequences. Now this is quite easy to work with. So I leave it to you to construct another subsequence which does this. I mean, it's obvious. I don't think there's much. Now, this aspect. So the question that you ask is from this experience on this example and probably on many other examples, one could ask the following question. Can you write this as a general theorem? This is exactly what the Riesz theorem conveys. Okay. So we will state the theorem. This fact general. So this is what we have. Now we give the statement of the theorem. And now I would also make a remark. You see that if you have a sort of similar situation that you often come across in analysis. Some phenomena is not true for the entire sequence, but possibly it is true for a subsequence. An example is this. Suppose you take a compact interval, something like 0, 1, and choose a sequence of points on infinitely many points. Okay? It may converge to a point, but certainly, even if it is not a convergent sequence, you will see that there exists a subsequence or more than one subsequence which converges. So the existence of converging subsequences you can see in that scenario. Then of course you have a broader version of this result for functions sequences, where you see that if you have the functions on a compact interval satisfy the property of what is called equicontinuity, then the sequence may not converge. However, there are bounded functions or continuous functions on the interval, on a compact interval, say 0, 1, 0. Then the sequence of functions may not be a convergent sequence. However, there are subsequences, it may not be one, there are subsequences which do converge to continuous functions. Now, these are all theorems of this kind, and this theorem, the Riesz theorem, is of this type. So, we will make the statement. If Fn converges to F in measure on E, a measurable set E, then there exists a subsequence Fn k that converges point-wise almost everywhere. Yes. Now this is the interesting. So convergence point-wise almost everywhere is there for subsequences, some subsequences, but not for the entire. So convergence. So this actually tells what we have observed on that example. That is proof. The proof is not there. Proof. So what we have is this Fn converges in measure. Then the consequences. Now this implies there exists a strictly increasing sequence of natural. Nk such that measure of the set f jx and by a, this is less than or equal to 1 by 2 or you just recall the definition. Okay, you recall the definition, put epsilon here, and what you do is, what is the definition? The definition, it is eta that you have used. Okay, for any eta positive, for a given eta, you have corresponding epsilon such that this is true. But this happens corresponding to k, you have a certain nk. Okay, so for all j, okay, so this is how you get a sequence of numbers nk. Okay, right. Now let us define give a notation Ek equal to set of all x belonging to such that one by k. And you know that the measure of Ek, so what we have asserted is that measure of is less than this is what we this is how we have picked up Nk, which implies the following: sigma k equal to 1 to c is finite because it is 2 to the power 1 by 2 to the power k, and this series sigma 1 by 2 to the power k converges. Now that makes it possible for us to apply the Borel-Cantelli theorem lemma which we have proved earlier. So let me just recall. Which we have proved earlier in one of the talks. So you can refer back to that and see what it means, but I will just quote the thing. The proof you can have a look at just to get this in mind. So Borel-Cantelli theorem, that's the following. Says that I am just quoting it. Let Ek be a countable collection of measurable sets such that is finite, then for almost all x belonging to R belong to at most at most finitely many of the Ek's. Now this is the Borel-Cantelli theorem. Now this is a typical scenario where one can apply this. because you see that measure of Ek is less than or equal to 1 by 2k, and this result is, so Ek's are such that this particular result is. So we have that is what you call this one. Let's designate by okay. By star. So this is the one that we are referring to. Now this collection Ek the assumptions of oral cantilever. Therefore, the conclusions follow. Okay. So, what does it mean? This is what we are looking. So, by Borel cantilever lemma, by this lemma, almost all x belonging to Ek, E belongs to finitely many E's. What does it mean? This implies there exists an index kx such that x does not belong to k Ek for k greater than or equal to kx. That is, when k greater than or equal to kx, it is going to be infinitely many Ek's. Okay. So this is what you have. Almost all x belonging to E belongs to finitely many Ek's. Therefore, almost all x in E belongs to almost all x. There is a corresponding kx that you can find such that when x does not belong to Ek for k greater than or equal to kx, what you can have is this mod f and kx the negation of this. What does this say? Look at the definition of Ek. Now you see, we are writing this greater than or equal to 1 by k. Therefore, the negation of that is less than 1 by k. For every k greater than or equal to kx. Now, this is true for each x, you have a corresponding kx. Okay, right? So, except for finitely many, okay, you have this property holding, right? What does it mean? This implies is equal to fx for almost all x. Because of this conclusion. Okay. Therefore, this is what you get. So, you have the subsequence f and k converging pointwise almost everywhere. Pointwise that proves it. So, that proves this theorem. Okay. Now, let us look at one of the consequences of this expressed in the corollary. So, the corollary is essentially, this is only a tool that we have devised and we have put it as a separate theorem because it's a powerful result. And this is used to, see that the convergence in measure is equivalent to Fn converging to 0 in measure E and Fn is uniformly integrable and tight over. So, no, we are showing the subsequence, converging this, okay, or is equivalent to these properties. So, let us state that. So, another theorems which gives you information about it, because eventually our problem is whether integration and limiting process can be interchanged. This is the question that you are asking. Okay. Very important one. Let Fn go to 0. Sorry, be a sequence of measurable functions non-negative on. So these functions are non-negative functions. They are also measurable functions. Then limit n tending to infinity integral equal to 0 if and only if the sequence Fn converges to 0 in measure previous results we have talked about Fn converging to 0 point-wise almost everywhere. Now this is a corresponding result with convergence in measure. And Fn is uniformly integrable and tight over. Now you recall there is a corresponding result earlier that we have proved. So there is integral Hn goes to equal to 0 as n tends to infinity has been, with this convergence in measure replaced by almost everywhere pointwise. Okay. Right? So what we have proved earlier, one of the corollaries that we have proved here, I will read it out with the same notation. Let Fn be a sequence of non-negative integrable functions. Okay. Right? Here it is just measurable functions. Integrable functions on E. Suppose Hn converges to, Fn converges to 0 for almost all x belonging to E. That is pointwise convergence. Then integral left. Limit n tending to infinity of integral Fn is equal to 0 if and only if Fn converges, Fn is uniformly integrable and tight over. So we were in that context working on this. Now here what you are saying is that all these things are the convergence in measure and then Fn is uniformly integrable and tight over C provided this integral. So here you see that since the limiting function is f identically equal to 0, this is actually because f is identically equal to 0. or at least almost every, right? So let us prove this corollary. So proof. Assume, because it is a necessary and sufficient condition. You have limit n tending to infinity of integral over E phi equal to 0. Then by the corollary to the general Chinese theorem, all the things would follow. I mean, this part would follow, but the other part we have to look at. Fn is uniformly integrable and tight over it. Now all that we have to show is this. Now it remains to verify that measure on it. So the other part follows from the corollary to the general Vitalis theorem. Okay. So only thing that we have to prove is that Fn converges to 0 in measure on E under these circumstances. Okay. Now we use the formula, but we apply Chebyshev's lemma. It's a very useful tool. Okay. We have an estimate that appears in Chebyshev lemma. So by Chebyshev's inequality, we have the following. This is the measure of is less than or equal to integral over E. This is the estimate that you have. Okay. Therefore, 0, because we are working on non-negative functions anyway, limit n tending to infinity of measure of yeah, is less than or equal to 1 upon eta into limit n tending to infinity integral over E. Okay. And now you know that by this assumption you can interchange the limit and the integration, since Fn sorry, yeah, since Fn converges to 0 and what you have, you can interchange the limiting process zero. Or I will do it this way. What I conclude is this. Now you know that this goes to 0. Therefore, you see, you have this result, that is now integral limit n tending to infinity Fn equal to 0 implies the following: limit n tending to infinity of, see, this is squeezed between 0 and 0, therefore it is 0. Measure of x belonging to E Fn x greater than eta equal to 0. That is, what do we conclude? That means Fn converges in measure 0. That's what we wanted to do. Okay. Now converse. So we work on the converse. On the converse, we assume the end part of the theorem, namely zero in measure one, two, uniformly integrable and tight. Over. That's the assumption that we So what we want to conclude is this. Claim zero. This is what we want. So we use method of contradiction. Assume integral limit n tending to infinity fn's are all non-negative. Therefore, this is positive. Okay. See, assume this means that this is greater than 0 because fn's are positive. That's the reason. Okay. If this is not equal to 0, then there exists some epsilon naught positive such that, and a subsequence we are using the power of the previous theorem, fnk for which is greater than or equal to epsilon naught. So what we have is now a subsequence corresponding nk. Okay. Now we apply by Riesz theorem. Apply to this subsequence, that is applied to fnk. There exists a subsequence of fnk which converges to f identically equal to 0 pointers. Almost everywhere, because see, fn converges in measure, therefore the subsequence also converges in measure. So the conditions that are required for the application of the Riesz theorem is satisfied if you take this subsequence. Okay. And this subsequence is uniformly integrable and tight. Therefore, we can apply Vitalis convergence theorem. So, apply the general Vitalis convergence theorem. And what is the consequence? The consequence is that such an epsilon naught does not exist. Okay. Contradiction to integral over E because you see that this goes to 0. Okay, this integral goes to 0. Therefore, there is a contradiction. Now that completes it. Okay. So we have explored all the consequences of convergence in measure. So all sorts of convergence we have now considered. Uniform convergence, convergence pointwise almost everywhere, and convergence in measure. Okay. It will be nice to sit down and compare these four various theorems that we have proved in this regard. Okay. All this, the objective is this. Okay. This is the one that you are seeing. Write this. It means that you can interchange the limiting process and the integration. Okay, right? So in general, suppose Fn converges to F, then you can work on F minus Fn. Okay? If Fn is a sequence which are say not necessarily non-negative, but this we should get Fn minus F minus Fn non-negative. If you have such a sequence, then this result can be right. Okay, thank you very much. With this, let us conclude this part. And now, what we intend to look at is the relation between Riemann integration and the Lebesgue integration. So that will be explored in the next few lessons. Thank you very much.